Good afternoon, Professor Bishai. We are really honored to have you here with us in the second issue of our magazine, Trends in Physics, مسارات في الفيزياء, published by the Arab Physical Society. Dr. Bishai, you have a very distinguished scientific career, indeed, working in some of the most active particle physics laboratories, first Fermilab with the Tivatron experiment, then working at Brookhaven National Laboratories, where you are now responsible for about 1,400 members of Dune collaboration. In addition, you have been involved in other neutrino experiments worldwide. For example, the Diabase experiment, for which you were jointly awarded the Breakthrough Prize in Fundamental Science in 2016. Also, you are a member, you are a fellow of the American Physical Society since 2014. Let me very quickly introduce our magazine to you. It aims to explain advanced research in physical sciences to the public. The Arab Physical Society and its magazine are committed to disseminate scientific knowledge, enhance public understanding of physics, and promote scientific culture in the Arabic world. I, Adel Awad, and with me, Dana Abdelghani from the editorial team of the magazine. We are really happy to meet you and have this interview with you. My first question, Dr. Bishai, is the following. Could you please give us a brief overview of your personal journey in experimental particle physics till taking the responsibility of being the spokesperson of Dune collaboration?
Yes, so I started my university career at the American University in Cairo. And then I transferred in my third year to the University of Colorado Boulder, and I finished my bachelor's in physics at the University of Colorado Boulder. At that time, my advisor was working at Fermilab, my career advisor, and I'd already been very interested in particle physics. So, I mean, I would say that, so then I transferred to Purdue University for my PhD, where I did my PhD research on the Clio experiment, which is based at Cornell, at a laboratory at Cornell University, where there was an anti-electron collider, and we were studying the properties of charm quarks. So that was part of my thesis. Afterwards, I transferred to Fermilab as a postdoctoral researcher, working on the collider detector at Fermilab. At the time, Fermilab was operating the Tevatron, which was the highest energy collider of the time, and I joined for the CDF collider detector at Fermilab, the second two, which was the big upgrade that happened in 2008. And I finished my postdoc there. And the research I did as a postdoc, I worked both on hardware. I was, one of the people in charge of commissioning the silicon detector for the CDF too. And I also did a measurement of the production of particles containing big quarks, which became one of the most cited paper from CDF2. Afterwards, I then became a staff scientist at Brookhaven National Lab, where I went from working on hadron colliders, so colliders colliding antiprotons as the Tevatron, to working in neutrinos. And I worked on the Diabase experiment, the Aminos experiment. All of these are different neutrino experiments. So Diabase experiment was an experiment based in China. I was not a big most of my involvement had been in what became the deep underground neutrino experiment, but I was involved with Diabase in the early years. and Chinese experiment studying anti-electron neutrinos from nearby reactors and studying their properties. And then I got involved for the last 20 years at Brookhaven Lab with from the very start, the growth from a concept by my colleague Milan Diwan and others at Brookhaven National Lab of a long baseline neutrino experiment based in the US to what is now the Deep Underground Neutrino Experiment, which is a large international effort that combined the efforts of people, of experimenters in the US and Europe and South America, Africa, into this very large international experiment based in the US, using a beam of neutrinos from Fermilab and detectors located 1,300 kilometers away in a mine in South Dakota. I would actually say that my journey in particle physics started when I was 15, when my uncle, who was Dr. Bishai, he was actually a biologist and a very famous biologist in Egypt. He specialized in the fishes of the of freshwater fish of Egypt. He wrote the seminal studies, and he was mentoring me in my biology classes. And he introduced me to the National Geographic magazine, which he had at the time. And I read an article about particle physics in the National Geographic magazine. And when I was 15 years old, it talked about the Tevatron and it talked about CERN. And so I decided that's what I want to do. And since many of my uncles and even my father were PhDs, and then that was the start of the journey. And I ended up being a postdoc at the Tevatron, and I still have that copy of the National Geographic magazine. And I thank my uncle for being one of the people who introduced me to this.
Yeah.
Well, I'm a physics graduate myself, looking to continue my studies. And I always wondered the graduation. So, caught your attention this. Just a bit, but yeah.
So, yeah, parents are
Oh,
right. So I started reading about physics and I was interested that one of the, after I transferred to the US as an undergraduate, I talked to my professors here and I applied for PhDs at institution already, in part on just my reading and my understanding of the differences between the fundamental and applied sciences. And really today, I think young people today, they watch YouTube, they watch TikTok videos, and you get your information from the internet. In my day, I was just lucky to have parents who bought me science magazines and science books so that I could educate myself, because we did not have access to the internet. And of course, programs like العلم that was playing on Egyptian TV, which I watched, which was mostly medicine, but I liked science, and I watched those programs. Very few of them that were available.
Yeah, that's awesome.
So our next question is about could you please give our readers an overview of the neutrino experiments you are involved in now, and what are their objectives, and how can we use these experiments to differentiate, for examples, between various neutrino models?
Okay, so if you put your hand out, you will have 10 billion neutrinos that are coming from the sun. So neutrinos are very light neutral particles that they are produced both in nuclear fission and nuclear fusion. And it's the story of neutrinos, of which Brookhaven Lab played a key role, and 2 Nobel Prizes were already awarded to experiments in neutrinos at Brookhaven Lab where I now work. It started out with an interest in using neutrinos to understand the sun, because they are very weakly interacting particles. You can actually look at neutrinos and the distribution of their energy spectrum from the sun and see what type of fuel is burning inside the sun. If you only look at the light from the sun, or light from galaxies, or other astrophysical phenomena, such as an exploding star like a supernova, you will only see the surface, what's happening on the surface. But if you want to see the processes that are happening inside the sun as it burns or as it explodes, that's where a lot of the interest in neutrinos started from. And through that study, a big detector was placed very deep underground so that it's shielded from cosmic rays in what was then called the Homestead Gold Mine in the state of South Dakota. So it's 1.5 kilometers underground, and this was the famous experiment done by Ray Davis. The very famous experiment done by Ray Davis from Brookhaven National Lab, in which he was studying neutrinos from the sun and counting the number of neutrinos being produced. There was a discrepancy, and that discrepancy, because we were looking for a chemical reaction that specifically looked at the interaction of electron neutrinos, that discrepancy and subsequent experiments in Japan, produced, I'm sorry.
Okay.
Produce the result that that neutrinos actually change from one type to the other. That coupled with discoveries that neutrinos come in several types. So at Brookhaven Lab, there was an experiment that discovered that there is a neutrino that comes associated with interactions that produce muons. That's called the muon neutrino. And then there was experiments at Fermilab that also discovered the third neutrino associated with the tau lepton, which is the heaviest of the 3 leptons: electron, muons, and taus. So now we know that neutrinos transfer from one type to the other because they are formed of, each neutrino has a flavor. It's an electron flavor or a muon flavor, an electron flavor, which means that when it interacts, it's almost always in the interaction produces, if it's an electron neutrino, an electron. If it's an anti-electron neutrino, an anti-electron. If it's a muon neutrino, then there was always a muon produced in its interactions, or a tau neutrino produces taus in its interactions. So these are flavors, and it turned out that the neutrinos we now know are each flavor is actually a superposition of 3 quantum states with different masses. And the masses of the different mix of quantum states corresponds to different flavors of neutrinos. So as they propagate, these masses move at different velocities, and the change of the quantum constituents of the neutrinos will change. And so then you can have flavors changing from one to the other. This is a very unique, this quantum interference quality is very unique to neutrinos because they're such low mass. And you can observe this interference on very long distances, even though the masses are very, very small. We're talking about the lightest, the largest mass difference. We don't know the absolute mass of the neutrino. We know it's less than probably half an electron volt. But the lightest, the difference between the third mass state and the second mass state gives you that neutrinos are at least between 50 milli-electron volts to maybe half an electron volt. We know the differences between the mass states. We don't know the absolute mass of the lightest state. So that is one of the things that we're trying to do. So right now, the study of neutrinos is more looking at how neutrinos mix and how antineutrinos mix, to try and see whether in the mixing of neutrinos and antineutrinos, there is evidence for larger asymmetries between matter and antimatter. We do know from the quark sectors, from the mixing in the quark sectors, which is much, much smaller than neutrinos, that there is a difference between the way matter and antimatter, but the difference is too small to explain why our universe is full of matter. So we're looking whether neutrinos have a larger asymmetry between the way they mix, the neutrinos and antineutrinos mix. And then, if there is a very large asymmetry, then, it could be a hint of what type of physics is leading to matter, antimatter, matter dominating over antimatter in the universe. So, but the first order right now, and the first push for these big neutrino experiments, including the deep underground neutrino experiment, is to look for this difference in the oscillation between flavors of neutrinos and antineutrinos, and also use the difference to look for, of course, the interference tells us what, whether the third mass state is heavier than the first one, or whether the first mass state is heavier than the third one. And what determines the first mass state or the second mass state is that, we know that particles come in generations. So electrons are first generation in the standard model of particle physics. Muons come from the second generation, and taus comes from the third generation. And so we know that what we call the first mass state of neutrinos has mostly electrons. So if we follow the model as in the quark sector, where the lowest generation is the lightest, then the second generation is heavier, and then the third generation is heaviest, that's what we call the normal ordering of neutrino. If mass 3, which has almost equal part tau and muon, which are the second and the third generation, is the heaviest, then they follow the same mass ordering as the quarks. If not, then it would be inverted ordering. And this is of interest because, everything about neutrinos is very different than the quark sector. The fact that they have mass is already physics beyond the standard model.
Yes.
The fact that the mixings are almost maximal between the different states is extremely, the quarks, the mixing are tiny, but they exist. So a lot of these kind of symmetries are very different. So we want to know whether the mixing is maximal in neutrinos. We want to know whether the mass ordering follows the same pattern as the quarks, or whether it's different. These are all the questions that we're trying to answer by studying neutrino oscillations in experiments like the deep underground neutrino experiment. And we also study these oscillations from, so in the case of the deep underground neutrino experiments and other and similar experiment in Japan, we're studying the oscillation of neutrinos produced from an accelerator. But we can also study neutrinos, as with the Diabet experiment, the oscillation mixing of these neutrinos over shorter distances of 1 kilometer from nuclear reactors. So in one case, we study muon neutrino and anti-muon neutrino oscillations produced from an accelerator. In the case of the reactors, we study anti-electron neutrino oscillations produced from reactors.
That's great. Next question is, did you face any obstacle in your career as a woman in science? And if so, how did you overcome them?
In general, you don't feel a lot of obstacles when you are more junior. I think it's not so obstacles, but differences in the way as you become more senior, and start moving into more leadership positions, there are differences in the way people react to female leaders and male, and even getting to those leadership positions. Yes. There are ways in which people react differently. Women leaders tend to have to prove themselves more, whereas we tend to have to justify our opinions more. So all of these things, you can count those as obstacles. On the other hand, I think it makes you a better scientist. If you're careful what you say, if you are more convincing, so that we should not be taking what somebody says as the authority just because, you know, they look a certain way or they are male versus female. We should always be questioned, and people should be able to express their opinions and express. And when as a leader, you should justify also the decisions that you're making. So I think that it makes us better scientists, but it is harder being a female leader than a male leader in some sense because of the you know, implicit bias that everybody has, including women as well, towards how leaders should behave and how they assert their leadership and their authority.
Yeah.
Okay. So my question is, did growing up in Africa, first in Nigeria, then in Egypt, affect your interest in science? In other words, did you feel like you have enough exposure to science as a teenager in Africa in general? And what advice you can give to parents to keep their youngsters interested in science in Africa?
So, so let me just say that, you know, of course, my generation, which is Generation X, as they call it, it was a little different. The opportunities for exposure were much less. But that being said, I went to elementary school in Nigeria, and I had an excellent mathematics background. So my school provided very good mathematical training. My teachers were wonderful. When I came to Egypt, even though at the time, you know, in schools, our curriculum is very fixed, you know, this is what it is, right? There's the way you teach science at the time when I was in school, this was the government curriculum, and the way you teach physics and math was very, you know, here's a problem, here's how you solve it. There's no opportunity to understand or question the concepts very well. That being said, my teachers were fantastic. I had very good physics teachers. I had very good math teachers who went beyond what was asked of the curriculum to try and get us interested. But primarily, it was my parents who supported us. I think today, most parents are probably behind their children. So yeah, because you know everybody is much more aware of what's going through because of our access to the internet, and so if there are much more opportunities also to learn. So I think the important thing is, so I'm also a lecturer at the African School in Physics, which is conducted every 2 years. Starting from 2000, a colleague of mine started this effort, which is joint between the US and Europe, where we go around and we produce lectures in fundamental physics. And the students I see come from, you know, we choose students that come from less privileged backgrounds. I came from a privileged background. I went to private schools. My parents were relatively wealthy. They were able to provide me with resources I could never have had otherwise. But what we're seeing is that because of the penetration of the internet, and if the children are exposed, even in a small way, to by the schools, by the society to science, they can then go and find their interest and go around the internet and look and learn and, you know, take classes if they have to. So it's much easier now, but I think we just have to start with introducing the concept and introducing them to where they will find these concepts. So things like, you know, when I was in South Africa, they had a wonderful science museum. And bringing students to these science museums, and where you can have a program of public lectures at these museums, so you can get schools. It doesn't matter from whether these are private schools or schools that are serving much less disadvantaged neighborhoods. Having that resource there, having scientists come and give public lectures, that is where you can grab the attention of a student, and then they can go off on their phone and find out more. But you have to have that initial that initial way of, and then this is where, you know, some of these programs that you can have that to just give them the ideas in a fun way. And that's the nice thing of science museums or lectures, is they're done in a way that grabs a child's interest, and it can be done as part of the regular school year, as part of the regular curriculum. And like I said, schools do not have capacity to have labs. They do not have capacity, but you can have these centers that you can spend a bit more money on, that brings people in and attracts and starts to attract them to what science is and how to engage better.
Yeah. Okay. What advice do you give to young physicists who aspire to build a career in science, especially women? And in your opinion, how can developing countries, specifically Arab ones, give women more support and opportunities to engage them in STEM?
So I think that I think there is a bigger hurdle in a lot of countries to, I think that engaging in things like medicine and engineering does not need any, that already is well, most countries are well positioned. I think there is a bigger struggle to engage in the fundamental sciences, because there is there's not a lot of understanding of what training in the fundamental sciences prepares you for. Our labor markets in the Middle East and Africa tend to be very specific. So I hire this person, they should have to know exactly this. In the US, the labor markets here tend to be, it doesn't matter exactly what you know. What matters is how creative you are and how well you know how to learn. So they're more interested in your thought process. And so it does require, and for our own cultures to advance, is this understanding that what fundamental sciences do is they attract and train a particular way of thinking and a particular approach that is much more flexible than being specifically trained to do, exactly this area. If even engineering has part of it which requires creativity to be able to advance and apply these concepts of fundamental science. So I think some of this is introducing the value of an education in fundamental science, but then also a realization that a lot of fundamental sciences, and I'm an experimental physicist, require and develop experimental skills that are more broader. They're not as specific as an engineering degree, but they are broader. And this is particularly true of particle physics. You have to know a little bit of electronics. You have to know a little bit of detector design. You have to know a lot about data analysis, and which is an area of great interest to our societies, is people who can be creative as to how to understand data and to analyze data, big data as we call it. It's a very good field to get training in things like advanced machine learning techniques, which again, because you're learning not the computer science per se, but how to apply it to a problem in a creative way that nobody else has used before. So part of this is getting people to understand that these skills are useful. And then when you engage young people, do it equitably. So no blinders. It doesn't matter whether you're male or female or what your background is, whether you come from a poor school or a rich school or whatever. It's talent is universal, opportunity is not. And so you need to, and actually you will find that the people who have less privilege sometimes are the most talented, because they're the ones that are more driven.
Yes.
So we have to find a way of identifying talent, and to do it in a way that is blind to who you are or what you are, or whether you're male or female.
Yes.
Good. So our next question is about neutrino, back to neutrino physics. And it's two parts. First, what was your favorite research experience, which you felt curious and most excited about? And second part, what are the future neutrino experiments in the coming decade? Like, were these experiments going to tell us more about the nature of neutrino, Dirac or Majorana, or about the mass hierarchy? Is it normal or inverted?
So I think that it has been equally rewarding and equally frustrating. So I was very lucky that I joined Brookhaven Lab right at the time when this idea of this what became the deep underground neutrino experiment was just starting to be developed. So it has been challenging because it's taken 20 years.
Yes.
Because this is a very a huge undertaking. It costs billions of dollars. It involves many countries. And so this it's very, very challenging. First, you have to. So my most I really loved most when right around the time that what was then called the long baseline neutrino experiment, which became DUNE. I was the project scientist for it. And so project scientist was the scientist who is there to connect the scientific collaboration and the scientists with the actual project. This, this very large billion-dollar project with its engineers and its technicians and its project managers. How do you translate what the scientists are trying to do into what it is we're trying to build? What are the requirements? What are the specifications? And then the engineers will tell you, well, maybe this can be done this way, or a civil engineer will tell you, or can you do it with a smaller detector, or how do I orient my cavern? And you have to bridge between the scientists and the actual project. So that was the most, and I was project scientist until about through the beginning of the deep underground neutrino experiment. So from the previous experiment, the previous concept to the development of the conceptual design of the deep underground neutrino experiment. So that was my most, I really liked that, bridging the gap between the engineering, the project manager, and the actual scientists and the science we want to do, and translating it into what we're actually going to build or need to build. So that was my, I think you said the second part is about the neutrino experiment.
Yeah, the coming, the future neutrino experiments and in the coming decade, and
Okay.
where we will be able to actually know more about the nature of neutrino and the mass hierarchy.
So right now we have so there are two major ways of addressing the mass hierarchy, which is also the way we call the mass ordering, which, like I said, is we want to find out whether the heaviest neutrino mass is the one that has the second generation neutrino flavors in it, or whether that's the lightest neutrino mass, which would be very inconsistent with the quark sector, where the mass of the neutrinos, the ordering follows, the up and down quark are the lightest, and then the charm quark are the second generation. So this may not be the same as in the electron and the neutrino and lepton sector, which the charged leptons electron muon tau, or the lightest is electron, next light is muon, third generation is tau, is the mass state that contains the most electron neutrinos, the one that also is the lowest or the lightest. So the mass ordering is important. There are two ways to address them. One, we can look at the ways muon neutrinos oscillate to electron neutrinos over long distances, and that's the DUNE experiment is going to be because of the very long distance, 1,300 kilometers. We can actually see the interference pattern, and it changes. So the probability, because electron neutrinos scatter off electrons in the Earth, it acts as a as a scattering the way you can have a scattering index in different liquids. It acts the same way, and so you can get an enhancement of muon neutrinos oscillating to electron neutrinos if the mass ordering is normal, meaning the mass third state is the heaviest one. The other way of measuring this hierarchy is to actually look at subtleties in the oscillation pattern. So the oscillation pattern looks like a sine squared. It follows a sine squared distribution, and where the phase of that sine squared distribution is a function of energy. And that is the approach of the Juno experiment in China, which uses reactor neutrinos, and they look at neutrinos that are about 60 kilometers, some very powerful reactor neutrinos, and then they look at the number of electron antineutrinos that survive. It has this wiggle in it, and they look at the phase of the wiggle. Very challenging, very different ways. They're very different, the two. And so we want to be able to measure the mass ordering in these two ways. And so within the first few years of Dune, which will turn on around 2031, we will have the measurement using oscillations of muon neutrinos to electron neutrinos over very long distances, looking at this enhancement through the scattering of electron neutrinos in the Earth, or we can look at the phase from Juno. And if we see a difference, then something else is going on when the neutrinos travel through matter, which would be very interesting. So but the measurement from Dune within the first 2 years will be a very large statistical significance. Juno, it will take a very long time because it's such a subtle measurement to reach the kind of the definitive measurement the way June is. So the exciting thing is the combination of these two eventually. But we think that to reach the definitive measurement, it will be Dune within the first first years of the next decade, and then we'll get the Juno starts to reach the same beyond the 3 standard deviation precision at the same time, and then we can see we can look at both of these experiments. So these are two very important ones. The issue of Majorana versus Dirac is a bit subtle. So here is whether a neutrino is its own antiparticle. So if the mass ordering is inverted, then there are these double beta decays. These are a specific nuclei when they decay and emit a neutrino can also absorb. If the neutrino is its own antiparticle, they can also absorb in an inverse beta decay. So what we call a beta decay is your regular radioactive decay where an electron is produced, but they can also, they're a specific class of nuclei that can potentially, if the neutrino and antineutrino are the same, emit an electron when they decay and then reabsorb the neutrino because it's its own antiparticle, and then emit another electron, but no neutrinos come out from the interaction the way they do in regular radioactive decay. So these double beta decay, experiments are sensitive below the limits of of the experiments just looking at trying to determine the neutrino mass by looking at how the highest energy electrons emitted in the decay of tritium. These are called the endpoint experiments. And so they're very unique, very difficult experiment to do. And if the ordering is inverted, which we would learn from Dune or eventually from Juno, then there is a possibility they would be very sensitive. The sensitivity of these experiments would mean they would produce a definitive statement of whether neutrinos are Dirac or Majorana, because we would observe the double beta decay, the neutrinoless double beta decay, which produces betas here mean electrons, which would produce a 2-electron signature. It's a very subtle measurement, but the importance of the inverted ordering meaning is that they can actually make a definitive statement with this 3rd generation of neutrinoless double beta decay. If the ordering is normal, then it could be anywhere, and it could be beyond the sensitivity of the next generation of neutrinoless double beta decay, and we may never know if the mass is small enough that they cannot be sensitive to this you know, double beta decay process without a neutrino.
Yes.
Okay. Next question is, in your opinion, what does the Arab world need to advance in science? Is it funding or education or raising the awareness of importance of science?
I think it's all three, and you know, one of the interesting things that, like I said, even though I was very honored to receive this this prize as part of the Diabe collaboration, I was only one of 200 people, and I did not have a major contribution to that experiment, but through my involvement in there, I saw, for example, when we started, how, you know, China, which is of course a huge country, would very developed very quickly in the fundamental sciences, and so and we've also, you know, we have developing countries that, like Brazil and India, that are kind of advanced developing countries that are part of DUNE, and we can see how their educational systems are advancing, and I think that the Arab world is a little behind in terms of fundamental science. It's not, money alone is not the solution. For one thing, all of these, particle physics is unique in a sense that you can join any of these huge experiments, whether they're at CERN or whether it's DUNE, or whether in the US, for not a lot of money. But you need some, right? You have to pay, for example, to be able to join, but you can have access to all of that expertise, to all of that data with a modest investment, right? But it can't be zero. And you know, most of the Arab countries will be like, well, you know, we're poor, give us this. No, you can make that modest investment. And this is, and particle physics is unique. It offers you the opportunity of joining as engineers, as not just as scientists. There's a lot of engineering that could be there. There's a lot of, you know, hardware design. There's a lot of computational sciences that scientists who can join this effort. But it does require a small, you know, you need to be able to travel. You need to be able to pay the common fund, which is, you know, a few $1,000s per PhD that is paid to be able to have access to the data and to be considered part. So the funding is not, in particle physics, there is that opportunity. It requires some modest funding. So we have to be, you know, willing to do that. And there are several African, Morocco, Algeria, Egypt, all have big involvement in the LHC, the Large Hadron Collider experiments at CERN, South Africa as well. We have even small countries like Madagascar and DUNE. So we already have these countries involved, but they don't always get the modest amount of funding that is needed to really, to send more students, to support them, to support their travel. It's not a lot, but it's still not zero. There's not a lot of understanding of the collaborative nature of particle physics. It's very hard justifying to a funding agency why I should be sending, you know, the several $1,000s so that I can participate in a CERN experiment, for example. So these concepts need to change, and they need to change because this is a great opportunity in joining these. And part of what needs to change is understanding that these are great feats of engineering and computational science as well as fundamental science, and that the skill set that you learn joining and participating in these experiments. But it has to be, you know, using that knowledge just joining is not enough. How you actually take advantage of that also requires more engagement and a stronger engagement and larger groups to participate and to contribute. And so that takes a while, but the first starts with convincing the governments that this is a unique opportunity, that for some funding, that is affordable, you can be part of an incredible feat of engineering and science and gain some very valuable skill sets that you can't gain anywhere else.
Okay, and back to particle physics again. So the question is learning more about neutrino physics in the coming decade is going to tell us more about physics beyond the standard model?
So neutrinos are already physics beyond the standard model because we do not understand why the neutrinos have
Yes, I guess the
yeah.
question be behind like the simple extension.
Yeah, the simple extension.
Yeah,
So,
like
so
the
even,
natural extension of the standard model.
so even this natural extension of the standard model has some predictions that we can test, but you know,
Yes.
people are looking for including in experiments like Dune and other experiments at CERN for things like what we call heavy neutral leptons, which could be part of these seesaw models that are extensions of the standard model. So I think that if we go back to basics, just to explain to the audience, the reason we say that neutrinos are beyond the standard model is because with the discovery of the Higgs particle, and the Higgs particle mass being very close to what was predicted by standard model from the masses of the W and Z bosons, the heaviest of the other bosons, we know that there's a mechanism by which particles get mass. But the neutrino is 2,000 times lighter, minimum 2,000 times, if not more, thousands of times lighter than the lightest particle, which is the electron, which means it cannot get its mass directly from the Higgs boson. So there are theories that that predict that there are these, you know, the neutrino is a neutral lepton, so there'll be a heavy neutral lepton that but it's sterile, it does not interact with ordinary matter, and then it's connected by new physics that we don't know, a seesaw mechanism, as they say, to the light neutrinos that we observe. So there are predictions that you might be able to see these heavy neutral leptons, and so experiments like Dune or experiments even at the Large Hadron Collider are looking for evidence of them. Could be also part of the SUSY particle landscape,
Yes.
which is slowly being rolled out. The biggest issue, of course, is the CP violation, which is what leads to matter-antimatter asymmetries. There could be, like I said, this looking at the neutrino oscillations. So you think of neutrinos as an interferometer. So you produce muon neutrino, it travels 1,300 kilometers, it oscillates to electron neutrinos. There are interactions in the Earth. So there are people that saying because it's traveling 1,300 kilometers to the Earth in an experiment like Dune, you could be sensitive to weak interactions that are much weaker than the weakest force known to us right now. And that could change the interference pattern. So think of it as an interferometer that's looking for new interactions, very weak interactions that would show up by changing the pattern of muon neutrino to electron neutrino to oscillation pattern, because it's an interference between quantum states, and maybe some of this matter interaction driven forces could manifest themselves as changes from what you expect to see given the current standard model of neutrinos. So those there are people who are looking that use neutrino experiments. Because neutrino experiments tend to be very large and deep underground, you can also look for proton decay. So actually, almost all neutrino, there's a funny history that the Nobel Prize winning neutrino experiments, like Super Kamikande in Japan, or started out originally to study proton decay, and neutrinos were background, and they ended up discovering neutrino oscillations, and then the neutrinos became the major physics, the new physics beyond the standard model. But we still look for proton decay, and protons, of course, they're predicted to have a very large lifetime in the standard model. If you see a single proton decay in any of these very large detectors, that is physics beyond the standard model. There are people who are looking for like dark matter annihilating, let's say, in the sun and producing neutrinos that you can detect in big neutrino detectors like the ice cube detector in the South Pole.
Yeah.
which is one of the most amazing neutrino experiments that you could imagine, looking for very high energy astrophysics cell neutrinos. You may also look for dark matter signatures that produce neutrinos. So those are other examples of very active areas where you can use these experiments to look for beyond the standard model physics.
Yep.
Well, a bit away from physics, in your free time, do you have any hobbies? I read somewhere that you're a fan of operas and classical music. Do you think having leisure time is useful when one is full-time submerged in science?
You cannot be a successful particle physicist without having a deep intellectual life, I think. To work and to become a leader of hundreds of people, you need to understand humanity. You need, and there's nothing better than, literature and the arts. And you also need, as a physicist, to have an active imagination. You need to translate the language of nature, which is mathematics, into concepts that a human being can understand to advance them beyond. And for that, you actually need a broad intellectual life that is beyond science, because that's how you develop the skills, not just the communication skills, but the imagination skills that you need to translate, this complex language of nature, which is mathematics, into, Feynman is very famous for taking these very complex, Richard Feynman, the famous physicist, he took these very difficult concepts, mathematical concepts that have to do with electroweak interaction. He drew diagrams, and he was very famous for, he went to Brazil for a year because he wanted to learn how to beat drums in the carnival, right?
Yes.
So,
Yeah.
so all of you will see that, Einstein liked to paint, Schrodinger was also, all of them had interests because of this deep connection between the imagination and which is what art develops. Literature develops understanding of humanity, which you need when you work with large numbers of people, and the communication skills. It's very important. Almost all of science, not just particle physics, tend to be on a larger scale. Almost all modern science develops through collaborative efforts, and collaborative efforts means human beings dealing with other human beings from very different backgrounds, and that is why you need a rich life to help you become a better scientist. And yes, I like opera, and I started. I was taking classical piano lessons when I was a child, again thanks to my parents. But at the time on Channel 2, I think every month there was an opera broadcast. So I watched my first opera on Egyptian TV. There were only 2 channels. And I got hooked because I already like classical music. But yes. And then when I came to the US and I was a graduate student, I would listen to it on the radio on Saturdays. They had broadcasts from the Metropolitan Opera in New York and then the Lyric Opera in Chicago. So of course I was too poor as a graduate student and was not living anywhere near a big city. So I would listen to the radio broadcasts. Now they actually have movie broadcasts, so you can go to a movie theater and watch the opera for much cheaper than an opera ticket, but at my time it was radio. So, and then it went from there. Now I can go and actually see these performances in person.
Yeah, that's nice. Yeah.
That's very nice, yeah. So this is supposed to be like a question from one of our readers. So amidst your many achievements, the award of the Breakthrough Prize in Fundamental Science in 2016, where you were jointly awarded this prize with the Diabay collaboration. What does the winning of this prestigious award mean to you?
So I think that, to be honest, it's more the fellowship in the American Physical Society that was directly a prize that I got for my work, both on understanding quarks and neutrinos. What
Yeah.
the Breakthrough Prize did, that was the first year it was awarded, I believe. It's the first time that a prize recognizes that our science is a collaborative effort. So even though I wasn't a major participant in the diabetic experiment by any means, I got awarded as part of this collaboration of over 200 people from everywhere. I mean, it was a project that was based in China, but it had people from China, the US, Europe, all trying to understand some very fundamental knowledge about neutrinos. And actually the result of the diabetic experiment was announced the same year as the Higgs, and both of these are considered 2012, the Higgs discovery and the measurement of the diabetic are both in our field considered seminal in that year equally. So I think that that's what the Breakthrough Prize means to me. It is the first time a major scientific prize recognized that science is a collaborative effort and that it takes hundreds of people to make a major achievement. Of course, there are people who are leaders who have, conceptualized it, but to make it possible is a very large enterprise. This is the value of that prize and what it means to me.
Well, thank you very much, Professor Mary, for giving us this great opportunity to have an interview with you. And thanks a lot for your time.
Thank you. Thank you for giving me this opportunity.
Okay.
Should we turn off the record?
Yeah, I think Sarah should.
Okay.